Hello again, and welcome to another Register HPC channel webcast. Or is it a podcast? I'm never quite sure. But one thing that I am sure of is that I'm Dan Olds, and that our topic today is pretty important stuff. Today we're going to be talking about power, about juice, watts, amps, volts. It's what comes out of the wall and makes all the computer magic happen, whether it's a supercomputer, enterprise computer, or even a PC or a set of workstations. In HPC, power consumption has become the major gating factor on the drive to exascale, and it's a challenge to a lot of HPC data centers in everyday usage, getting to petascale, new systems, all of that. It's also become one of the major operational cost elements that they really need to pay attention to. Improving power efficiency is the key, but as we allude to on the slide, you can't improve what you can't accurately measure. And when it comes to talking about measuring it, that's where our guests come in. Today, we're really lucky to have Eric Strohmeyer with us and also Natalie Bates. Eric, you may have heard of. He's one of the authors of the Top 500 list and leads future technologies at Lawrence Berkeley National Laboratory. Natalie has been all around the industry and works both with Lawrence Berkeley, but is very important in this energy-efficient, high-performance computing working group, the EEHPCWG, for those of you that want to just use the acronym. And we're going to be talking to them about some of the new proposals to bring more consistency, more accuracy, better precision to power measurement. Say hello, Eric and Natalie.
Hello.
Hi, Dan, and thank you very much for hosting this.
Great. Let's jump right into this with a complicated chart. Eric, what's this telling us here?
This is a chart developed by the DARPA Exascale study under the leadership of Peter Koji about 4 years ago, and it shows the progress we have made and we are expecting or hoping to make in terms of the compute power for the largest scientific supercomputers. So on the left-hand side, you see blue dots, which represent the performance of the 10 largest systems as recorded twice a year in the Top 500 project. And you see that it is a pretty steady progress over time on this exponential scale, which reflects Moore's law and the usage we have from Moore's law. Now, going forward, a couple of years ago, this study basically said, can we expect this trend to continue naively, as the dotted blue line would assume, or are we going to face some unexpected challenges? What are going to be the challenges for the next decade up to 2020 for the progress in computing system power? And what that study group did is they made two sets of assumptions, one which was very simplistic and one where they tried to really address all the upcoming challenges and potential bottlenecks in terms of system design into the future. The simplistic assumption is the green line, and you see for quite a while, at least till the middle of the decade, that we would, under these simplistic assumptions, would see an improvement in compute power as we have seen in the past. But towards the end of the decade, we might actually fall off that trend. And that gap you see on the right-hand side between the green and the blue line, that is actually already one order of magnitude, a factor of 10, and that is already quite substantial. Now, if we actually take the more stringent assumptions, where we take all the limitations we see in computer system architecture coming up, and especially include limitations we see due to power consumption, then we arrive at the orange line, and there we see on a more realistic assumption that by 2020 we would have fallen behind by at least a factor of 20 in terms of how much compute power we can use compared to what we would naively expect. So that would really change the way we would do computing, because we couldn't rely on the next computer being much more powerful than the last one had been if we really end up on that orange curve.
And much of what's really constraining this is power, as you point out on the box.
Very, very much so. The big constraint, it turned out, for the orange line is the power consumption of individual components on a chip, off-chip, and as well as whole systems. On all these levels, we're going to be restricted by power consumption. Individual components on the chip, we cannot drive them or use them as fast as we would like to, because otherwise, with higher frequencies, they use more power. Whole systems, we cannot, or whole chips, we cannot drive. We cannot use all the functionalities on the chip at the same time. Otherwise, the whole chip gets too hot. And whole systems, the power consumption of the whole system just becomes so staggeringly high that we couldn't afford actually running the whole system at a single point of time.
Which takes us, that's a nice segue to the next slide that talks about the cost.
Yeah, hand in hand with increasing power consumption for the whole system, as power actually doesn't get cheaper but gets more expensive, if anything at all. With the increasing power consumption for the overall system, of course, the budget you have to have and the money you have to spend for running your computer system is increasing. And we're getting close to the point that the cost for the electricity for a 3 or 5 year span to operate a big computer system might actually be comparable to the cost of the computer system itself. So the electricity costs, the power costs, are no longer negligible and are actually becoming very important for procurement and for design decisions, how we build computer systems and which computer systems we might buy.
And on the chart we appended, just so people listening at home understand, that the biggest supercomputer in the world right now, the K computer, as measured in November of 2011, currently consumes about 12.6 megawatts. Average top 10 computer, 4.8 megawatts. And at least by the sort of simple calculations I did, K computer's pretty energy efficient compared to the rest. In fact, I think it's close to the top. But that's still just a hell of a lot of power.
It actually is. As we go to newer technologies, our technologies actually become more and more computer efficient. It's just that the pace at which the overall computer system grows outpaces the pace at which we increase our computer efficiency. So overall, the power consumption for the whole system still grows, even though the system becomes more and more efficient. So it wouldn't pay off to use older technology. Older technology is less efficient. Definitely new technology is better. But even so, if you want to stay on the curves we have been in the past for increasing our compute abilities, we're going to end up with increasing power consumption. And the red line on this curve was actually from the same study from 2008, and they pretty much predicted the power consumption for the K computer for the number one system in the vicinity of the level where the K computer is nowadays.
Yeah, so it is pretty much right on that curve.
It's pretty much right on that curve, yes.
And how do we address this, though? And this gets back to the original point that Natalie made in one of the calls we were pre-calls before setting this up, is that you can only improve what you measure.
Yeah, we know that any engineering or design exercise requires being able to measure, and we've had many years now in measuring performance capabilities of our systems, of our computers, but we have not had the same focus on power and energy consumption. And so we are in the process of having to rapidly develop the capability to be able to understand the energy and power consumption of our data centers and of our systems.
And there are some data center measures that are out there, and some computer system measures as well.
Yes, the data center has, thanks to the Green Grid actually, we have a host of measures and metrics for the data center, like power usage effectiveness, PUE, and energy resource effectiveness, ERE. The compute system has been more difficult and slower to adopt measures and metrics. Everybody feels the need for a workload-based measurement, and some work is going on here in a lot of different fronts. Our focus is on HPC.
And what we're going to be talking about today is at the compute system level. even though your group is doing work on the overall problem.
Yes, we're working on both the data center and the compute, but yes, today's effort is on the compute system.
But at least we've gotten to the point where we're not just taking a look at the tag on the back of the system and figuring that that's the total power consumed by it. We've gotten past that point at least. But let's talk a little bit on this next slide with both of you about the different measures, and I guess sort of the problem here, and that there are so many different ways to measure power use and power efficiency.
Yeah, so the issues with measuring power for a computer system, there are several issues. One issue is, of course, what is actually part of a computer system. At home with your PC, that might look simple as a question, but in a big data center, that question isn't that obvious, because big data centers have multiple compute systems, and they might share some resources like central storage facilities and so on. And you might also have some features like additional cooling units which are attached to a single system, but which are installed after the system was delivered. So the question at the end of the day is, if you have a data center and you want to divide it with lines, demarcation lines, in individual systems, what is part of the system and what is not part of the system? The overarching goal here, of course, is that at the end of the day, if you talk about data centers, and if we divide it up in individual component systems, then if we add up all the individual systems, we should arrive at the same power consumption the data center as a total has. So we don't want to lose anything.
You don't count things twice, and you don't miss anything.
Exactly. We don't want to count things twice. We don't want to miss anything. So that's one of the big issues there. The other issue there is that different systems, different components, such as the compute part of a big computer system or the storage part of a big computer system, they might actually need different metrics and different workloads to be measured. So we can measure how fast the computer runs by gigaflops or petaflops, but we cannot measure how fast or how useful a storage unit is by any of those metrics. We have to have different metrics, and the different metrics also means we have to have a different workloads and things like these. The other issue here is how do you actually measure power? Mm-hmm. And the question there comes down to, do you do instantaneous power draw measurements? Do you do actually aggregate energy measurements and things like this? So we also have to be specific where and how power is measured.
And we're getting deeper into that in this next slide, is that, the sort of the prescription is to get some agreement and get common use centered on particular workloads and the methodology and the metrics you pull out of those, right?
Yes, that's exactly some of the issues we have in the working group and we have to address in the working group. We have to identify what are the parts of a compute system or a compute center which we want to measure, what are the appropriate matrices, and how we're going to measure power and the speed of the component, what is the appropriate methodology for doing our measurements. Only if we get these issues, if we get these definitions right from the get-go, do we actually have a chance at arriving something which is going to be useful for evaluating energy efficiency of individual systems, which gives builders or users of these systems some feedback of where they are with their efforts to be power efficient compared to their peers, and which is going to be useful in procurement and in architectural exercises when you have the question, how do you properly build energy efficient computer systems, and what is the right system for you to buy for your type of workload.
And I think something, Natalie, you and I talked about earlier, is that when this becomes factored into procurement decisions, that's when it's probably really going to spark some changes?
Yes. Well, the vendor community has been very involved with this effort and are part of the working group But I think that definitely as people ask for it through their procurement process, that's when the rubber really hits the road. And so, I can imagine at some point, requiring a certain efficiency of the system as well as a power number. That I think will really help to, again, accelerate this change that's required.
And if, the procurement departments specify a particular way to measure that energy efficiency and a way to report it that's standardized, that'll probably help a whole hell of a lot, too.
Definitely. Yeah.
This next point, we talk about who all is collaborating here. I mean, everybody I know knows the EEHPCWG. That rolls off the tongue. I mean, that's a common knowledge. But some people may be familiar with the top 500, the Green 500, and Green Grid as well.
Yeah. So really, there's a lot of people since the middle of 2000. There were a lot of people the decade. There were a lot of people who are starting to worry about power, and a lot of efforts going on simultaneously. But again, the effort wasn't coherent and focused for HPC. And so we pulled together a collaboration between some key players, the top 500, the Green 500, the Green Grid, primarily being enterprise-focused, but having a lot of traction on energy efficiency with a broad community and certainly all the same vendors. And then the EEHPC Working Group, which is a bunch of technologists who are passionate about energy efficiency, all working together to try and as change agents, to try and change the industry, the pace at which we're adopting energy efficiency. And we created a sub-team. The EEHPC Working Group is actually a broader group working on a variety of things, but we created a subgroup focused on this particular effort, which was to improve the methodology, metrics, and workloads for compute system energy efficiency. And we've been going now for actually about 2 years, and reporting regularly at both supercomputing and ISC, and we'll be talking more about that in a minute.
And I guess something I'd point out here is it's not like these four main parties plus the vendor community and everybody else, it's not like they're at odds here. The way I sort of understood it from our pre-calls is that if you look at this, the top 500 and Green 500 are very interested in reporting and tracking energy efficiency, but it's more the Green Grid and the working group that are deeply interested in standardizing the methodologies and the metrics and what's reported and finding new ways, better ways to do it. Is that reasonable?
Yes, the groups which came together here are actually very different. The top 500 is a very small group of people who collect and publish and analyze data about the HPC market for the last 20 years. So this is a very lean but very long-running effort, while the Green Grid or the HPC Working Group, they are typically working groups where you try to have the majority of the expertise on the table, trying to come to an agreement how to measure and how to report something. So those are very broad but much shorter-lived efforts defining something. So in a way, they both need each other. The top 500 needs the expertise from the working groups and from the Green Grid to make the right definitions, what to measure and how to measure it. And the working groups need efforts like the top 500 and the Green 500 for them taking those definitions and using them and publicizing them and carrying them forward for a much longer time than the working groups typically exist.
That in publication, the top 500, Green 500, is going to prompt more people in the vendor and customer community to actually do the measurements.
Definitely.
Yeah, that's the overall idea. And even that is not a given. Even in a project like the top 500, just because the top 500 wants to publish something doesn't mean that the users or the companies are going to give us the numbers. there still has to be a strong interest of the community, which basically encourages the companies to publish their results. And after a while, of course, something like top 500 gets enough momentum and then goes forward by itself. But getting something like this started definitely needs the community and needs the involvement of something like the Green Grid or the HPC working group to have that broad momentum from the community behind it. Otherwise, the top 500 itself would have a hard time to get something like this started.
The working group, by the way, is about 250 people, over half of which are from national labs, very much DOE focused. But we also have about 30% of our membership is the vendor community, and then we represent actually 16 different countries as well, and we also have academics involved. So it's a very broad community. It does reflect a big spectrum, but between the international focus and the DOE lab, the national lab focus, it represents a very strong part, a very large part of the supercomputing community.
Good. Let's talk get a bit more specific here with the proposed workloads and what we're really trying to do here.
Of course, one of the first questions when you have a metric which measures something like ability, capability, or speed of a compute system component compared to its energy consumption, one of the first questions is that you have to have a measure for what the capability of that compute component is. And that is a discussion which has been in the HPC community from the very beginning. What is an appropriate measure for measuring computer speeds or compute abilities? That is a discussion that has been around for a long time, and we decided early on in this effort that we are going to really focus on all the energy-related aspects and not necessarily on the workload-related aspects. We didn't want to repeat all the discussions other people have about how to measure computer performance. So we decided to go with some of the more broadly adopted standard benchmarks as workloads, at least for the beginning, and use those. And if people desire to use different workloads, they might do that as long as they stick to our methodology for their own purposes. So the most widely used HPC benchmark for better or for worse is the HPL, the High Performance LIMPAC benchmark. The High Performance LIMPAC benchmark basically measures the speed of the numerical computation when you solve a linear system of equations. And it has a few very nice properties. You get better speeds if you solve larger system of equations. So to show good numbers, it forces you to really use your whole computer and uses all the memory you have on your computer system. So that's a nice feature, and that is what the LIMPAC benchmark at the end of the day actually does. It really is a measure for how fast you compute do numerical floating point operations, how fast you can access your memory before regular memory access, and to some lesser degree, how fast you can communicate within your machine. So that was the first workload we adopted. Because in the HPC community, the numerical compute power is one of the dominant things we care about. And HPL is, in a way, the least common denominator in measuring actual compute power. We also adopted some of the other HPC benchmarks as workload to focus more on other components. One which was a little bit easier is a second benchmark called random access, which measures so-called GUPS, giga-updates per second. It's a benchmark which measures how fast you can randomly access the main memory in a computer system. So it has a very different memory access pattern from the HPL LIMPAC benchmark and complements it in that fashion. We do need additional workloads for additional subsystems. One which has been a little bit the junior for a long time in the HPC measurement community is I/O, the storage facilities. How do you measure I/O speeds, the access to your storage facilities? And we're working with some other groups there to come up with a more standardized benchmark workload for actually measuring that. With storage, the workload really tends to depend heavily on what the type of computation you run, what type of usage your computer system sees. That's why there's a less of a standardized benchmark for measuring workloads on a storage system these days.
Very good. And actually, I ran some LIMPAC myself just out of curiosity and found out that my wife's desktop computer, she works with me in my little business here, 24 times faster than a Cray 2. And much better price performance and energy performance as well.
Yes, that's one of the fun things to do with HP Olympic, compare today's systems with supercomputers of 10, 20 years ago.
And I was even running it with Windows.
Yes,
it's probably even better yet.
Yeah.
So some of the methodology that we're talking about, that's one of the big changes here with what you're going to be proposing is how to standardize that methodology in order to keep it easy enough to use and yet precise enough to provide accurate, good quality, usable measurements. Let's talk about that a little bit.
Yeah, one of the big issues we always face when we try to come up with a new common measurement and publicize that is that we need to get people to adopt it. And that has two conflicting sub-goals in it. People are going to adopt something if it's A, easy to do, and B, if it's actually meaningful. And unfortunately, these two incentives, they pull you in different directions in a lot of cases. So in our case, that means we decided to define for now 3 levels of accuracy of power consumption measurement, of energy measurement. The first level is really meant to make it easy to get a result, a measurement, even if you haven't set up your whole center for measurements like that in the past. So the first level is more lenient, is meant to help adoption of the overall process, while the third level in particular is really the state of the art in how energy consumption of computer system components is measured. We really try to have an as precise view of what the computer system uses in terms of power when we do a level 3 measurement.
And let's take a look at what those levels really are, what they mean in the real world. The differences between the first level, which is just a portion of the run, and also just a portion of the hardware, right?
Yes. So some of the differences we have between the different levels is obviously that in the easiest level, in the level 1, we are allowed to measure the power consumption only during a part of the run, about 20% of the runtime. And that is an approximation, especially if you know that Olympic the Olympic benchmark actually changes its power consumption from the beginning to the end. It tends to use more power at the beginning and less at the end. So we need to know where the power is consumed and things like this. But we allow you to measure only 20% of the run. You have to do the measurements during those 20% at least once a second or something like that. The other simplification for the measurement is actually that you're allowed to only measure a part of the system, or 1/64th to be precise, which might be only a single rack if you have 50 rack, a system of a size of 50 racks, and scale up the measurement from that part of the machine. That is obviously meant for somebody who hasn't set up their computer system for an overall measurement and just wants to instrument the single rack for a measurement and make it easier for them. So that's the spirit of getting people with a minimum effort, some number which makes sense, which allows them some comparison, but is not necessarily as precise as we would like to see it. If you look at the other extreme, the level 3, there you see we really ask that you do the measurement for the whole run, the whole 100% of the run. You actually have to integrate the energy, not just do instantaneous power measurements, but actually integrate the energy used during that run. And you have to give us multiple data points, what the energy consumption at particular points in the run was. So we see how energy consumption changes during the computation. And you have to do it for the whole machine, not just for a part of the machine, and include all the components the machine needs for doing the the calculations such as interconnect and things like these.
And then we also, as we're going to see on the next slide here, proposals for measuring the AC-DC power conversion process and the losses inherent in that.
So that is a subject which is coming up strongly in the recent history, that in 5 years ago or before that, most computer systems had their power supply on the board, on the individual node, and whenever you measure the node or a rack, you implicitly included the conversion losses from AC to DC power. Nowadays, we have a trend to reduce those losses, and one way to do that is to actually have a big power supply outside the cabinet, which converts AC to DC for a whole rack, let's say, and then get the DC power directly to that rack. And at that point, if you have that set up, you can easily measure power at the rack level, at the DC level, but of course that would not include the still noticeable power losses due to the conversion. So we have to have rule these days how you measure, how you report the power losses of external power supplies. And again, in the spirit of easy adaptability and precise measurement, we have 3 levels. The first level, where you're allowed to use data measured from the supplier of the power supply, up to the most precise level 3, where you have to do a measurement, and it has to be a recent measurement on the actual power supply. So it is actually fairly close to what the power supply is actually using at the run.
Very good. So, Natalie, in terms of getting this off the ground and getting it going, where are we at now?
Well, we have a methodology, a documented methodology, and we are testing it. We have the methodology is under review. It's been sent out to the working group. It's been sent out to technical committee on the green grid, and so we're getting feedback that way. We are also using it. We have 5 different early adopters that are using it during their very substantial WinPAC runs. Again, this is a pretty big time commitment to be able to run HPL. So they're out there collecting the power. Most of them are trying to attain a level 3 power measurement. We have Lawrence Livermore National Lab, Leibniz Supercomputing Center in Germany, Oak Ridge National Lab, and Argonne National Lab. All the national labs are U.S. DOE national labs. And then from Canada, we have Université Laval, Calcul Quebec, and Compute Canada. That's actually one name. It's a sort of a consortium organization, one system.
And
nice job on the French pronunciations, by the way.
Oh, thank you. And by the way, these 5 early adopters represent 3 different vendors as well. So we have IBM systems, Cray system, and it's actually a Sun system. So.
Did you say Sun?
Yes. The one from the Canadian is an older system.
Okay.
Yeah.
So they're going with the biggest thing that they have.
That's right. Exactly. Okay. And they'll be providing, these early adopters will be providing feedback, so the document being reviewed by the broader community as well as the early adopters will review the kinds of feedback that we get. We'll present it at ISC to the broader community there as well. And so we're hoping that this webcast goes out to the community of people who might be attending ISC, and we're encouraging you to come hear more from the actual people who are using it at the BOF that we have, where we'll be reporting on the measurements that are being taken right now as we speak using the new methodology.
So we're going to see that in, about 3 weeks now, almost a little less than 3 weeks now. Will there also be some results online for the people that can't be at ISC? Will that be coming out soon?
Yes. So thank you. The EEHBC Working Group has a website. The URL is on this last slide. And we always post our the latest information, all the presentations. The methodology is actually on that website as well if you're interested in going and looking at it. So we keep all of our information there. The working group is open to the general public. Anybody who has an interest in energy efficient high performance computing is welcome to join.
Great. Well, I really appreciate the time. This has been very informative.
Thank you very much.
Well, thank you very much, Dan, for having us.
This is going to have some serious and good implications down the road as more in as we get a consistent methodology and consistent set of measurements. Then I think the pace of actually seeing improvements come about is going to accelerate, and that's very important.
I totally agree.
Good work, and thank you guys for doing it. And we'll keep in touch, and I'll be sure and put out an update. And maybe we'll schedule another call right around the time of SC12. Talk about what's happened in the preceding few months.
Perfect.
Well, that would be great.
See you in Hamburg.
See you in Hamburg, yes. And on that, thank everybody out. I want to thank everybody out there for listening, and thank my guests today. And watch this space for more updates on this exciting and powerful, that's the first time I've used that pun, I hate puns, topic. Thanks again.